Bismillahirrahmanirrahim. Assalamu alaikum. Our today's lecture is about decimal adder and we can say BCD adders, binary coded decimal numbers. Mm, Computers or we can say calculators perform most of the arithmetic operations directly in the form of a decimal number system and represents the answers and also in the form of binary coded forms. As we know that when we enter the values in computers or calculators, those values are always in the form of decimal digits. And but these systems, when the decimal number system represent decimal number in binary coded form, that, that we said BCD form, binary coded decimal numbers form. An adder for such a computer must employ arithmetic circuits that accept coded decimal numbers and represent results in the same code. For example, we can say that for binary addition, it is sufficient to consider a pair of significant bits together with a previous carry that we need sufficient bits to add up and to represent the results. As we can see in this table, a decimal adder requires minimum of 9 inputs and 5 outputs. So, 9 input bits and 5 output bits, and from these 9 input bits and 4 bits are required to code each decimal digit. To represent each decimal digit, there are 4 bits which are required, and the circuit must have an input and output carry. There is a wide variety of possible decimal adder circuits depending upon the code used to represent the decimal digits. Here we will examine a BCD adder to perform the we can say arithmetic addition of any two decimal digits which are represented in BCD form. Uh, the operation requires uh, input bits we can say together with an input carry from a previous stage. If two decimal digits in BCD are required, then an input carry is also required from the previous stage. Since we can say in each digit does not exceed the value of 9 and output sum will not also increase from the will not be greater than we can say if an input digit cannot increase the uh, number of 9, so the output will not also increase, we can say 9 plus 9 plus 1, which will be equal to 19. So we can say that input input digit should not have to increase the value of 9 and output will not increase the value of 19. As the two digits are added, maximum value can be 9 plus 9 18 and one previous carry which is added. So we can say that output cannot exceed the value of 19 in the sum as one is being an input carry. Suppose we applied two BCD digits to a 4-bit binary added to add them, and the adder will form the sum in binary and produce a result that ranges from 0 to 19. The range will be 0 to 19 when we use the binary adder to add the numbers. These binary numbers, as we can see, are listed in the in this table. Are labeled by the symbol we can say K, Z8, Z4, Z2, Z1. K is the we can say carry, and the subscripts under Z, which are 8, 4, 2, 1, are the weights of those numbers, and that can be assigned to the 4 bits in the BCD code. The column under the binary sum list the binary value that appears in the outputs of the 4-bit binary adder. The output sum of two decimal digits must be represented in BCD form, as we can see in this column, and they should appear in the form as we can see in this column under the BCD sum. The problem here we will face during this addition process will be to find a rule by which the binary sum is converted to a correct BCD sum. As we know, we have already studied in the section of BCD numbers in first chapter that when BCD numbers increase from the value of 9 uh, greater than or equal to 9, 10 or greater than or equal to 10, we can say. So there is an error occurs. So to remove that error, we have to generate or develop a circuit which will correct this uh, inequality, or we can say the to correct this error which occurs in BCD number. So when the binary sum is greater than, we can say 1 double 0 1 1 double 0 1 when the binary sum is greater than this, we obtain an invalid BCD representation. The that BCD representation will be invalid, as we can see here in this binary sum. These are the will be the invalid BCD representations. So an addition of binary number 6 to the binary sum will convert it to the correct BCD representation and produces and will also produce an output carry as required for the, our operation. So when we will add a value of 6 in the incorrect non-valid BCD representation, the addition of 6 to the binary sum converts it to the correct BCD representation and also produces an output carry, as we have already discussed. And we can say why we add this 6 in the invalid BCD presentation, as we can say that the carry generated out of the 4-bit binary number is at the 5th place, and which is equivalent to the 16. It is actually the difference of, and carry generated from the decimal number is equal to 10, and the carry generated in the binary number at 6th place is equal to 16. So the difference between these two carries is equal to a 6. So this difference 6 is converted into binary form, and then this binary number is added to the incorrect BCD representation, and that then to correct the BCD representation, and that also produces an output carry as required. And we can say that to distinguish these BCD numbers from binary 100 and 1001, which also have a 1 in position Z8. So to distinguish them from, we specify further that either Z4 or Z2 must have a 1. Z4 or Z2 must have a 1, as already Z8 position when we have to generate a carry, that carry to produce that carry, we can see in this table. We know that this Z8 is equal to 1, and but for the valid BCD representation numbers of 9 8 and 9, they also have a Z8 equal to 1. So there is another specification specify further that either Z4 or Z2 must have a 1 to find out the carry signal which is generated at the output, and which will show us that either the BCD representation is correct or incorrect. When this value of carry is equal to 1, we will see that the representation is invalid, and then we will add the 6 in the BCD adder. It is, and this is the implementation of BCD adder, and this is a circuit you can see Here we will add the two numbers augend and addend of each of 4 bits, and this is for input carry, and output carry k is generated from here, and the secret of the carry which we will construct from this equation will show us that how we have to find out the carry output, and that equation of output carry is implemented by using two AND gates and one OR gate. So here we can see that this output is equal to, if we copy that from the previous place. So here we can see that this output carry, which is C, is equal to K plus Z8 into Z4 plus Z8 into Z2. So here Z8 and Z4 are multiplied by using this AND gate, and Z8 and Z2 are multiplied by using this AND gate. And then output of these two AND gates and the output carry of 4-bit, first 4-bit binary adder are added by using this OR gate, and the output carry is generated. And we say when this output carry is equal to 1, it will show us that the BCD representation is invalid, and we have to add the value of 6 in that invalid representation to correct the BCD value. And then we use this 1 to generate that 6-digit binary number to add in that incorrect BCD value. And after adding this 6, it will generate a valid BCD number. The output valid BCD number will then be equal to a valid BCD number, and the output carry will be equal to 1, as this output carry can show us that which is generated from the bottom address can be ignored, as we can consider this output carry as equal to 1, which is so the carry generated from this 4-bit binary adder can be ignored easily. A decimal parallel adder that adds n decimal digits needs n BCD adder stages, and the output carry from one stage must be connected to the input carry of the next higher order stage, and so on. We can increase the number of BCD adders, whereas we can here say that if n BCD adders we have to generate for n decimal digits, we will for the adder for that n decimal digits will require n BCD adders, and the carry from each BCD adder will be transmitted to the higher order stage and will be added at that stage. So if we can say that simply we can as we have also studied in the chapter number 1 that how we are added and how we transmit these things, and this is the implementation of a BCD adder which is used to add BCD numbers and show that how computers and calculators perform the arithmetic operations behind the screen. So take care students, inshallah we will study in our next lecture about BCD multipliers, or we can say binary multipliers, and these binary how they work and what are their operations we will study inshallah in our next lecture. Take care. Allah Hafiz.